In this session, we will be solving some of the problems, gate problems of mechanical operation. So, say this is the problem, 2 marks problem. The particle size distribution of feed and collected solid samples for the particle size distribution of the feed and collected solid for a gas cyclone are given. So, what is that? It is given size range, weight of feed in the size range in gram, weight of collected solid in the size range gram. Now, the size range is in micron, 1 to 5, 5 to 10, 10 to 15, 15 to 20, 20 to 25, 25 to 30. So, these fractions are given. Sorry, this is size range, and this is 2, 3, 5, 6, 3.0, 1.0. And this is 0.1, 0.7, 3.6, 5.5, 2.9, 1.0. So, it is asked what is the collection efficiency of the gas cyclone. Right. So, in percentage you have to express. So, this much amount of feed we have and the collection efficiency we have to calculate. So, first we have to note that okay, so collection efficiency is basically the fraction of mass collected over a size range. Now you see this collection efficiency of this 0.1 for say this is I 1, 2, 3, 4, 5 and 6, right, and weight of the feed, let us write MFI and here MCI. So, eta I for individual fraction we can calculate the collection efficiency as collected mass divided by mass in the feed, right. Like for individual we can calculate the collection efficiency as 0.1 divided by 2, 0.7 divided by 3, 3.6 divided by 5, 5.5 divided by 6, 2.9 divided by 3, 1 divided by 1. So, individually we can calculate the collection efficiency. Now, this collection efficiency we have to take an average and that must be the mass fraction weighted average. So, eta overall is equal to summation of xi into eta I, where summation xi is the mass fraction of that material or that size range in the feed, right. So, it is MFI divided by summation of MFI into eta I. So, I equal to 1, 2, 1, 2, 3, 4, 5, 6, 1, 2, 6. So, that will be my answer. So, it is basically a problem of averaging, but we must know what is the collection efficiency formula for the cyclone. So, you see this 2, 3, 5, 5 plus 5, 10, 10 plus 6, 16, 16 plus 4, 20. So, here the mass fraction we can calculate 2 by 20, 3 by 20, 5 by 20, 6 by 20, 3 by 20, 1 by 20. So, individual eta must be multiplied by the respective mass fraction of that size range in the feed, and therefrom we will get the overall collection efficiency of that cyclone. Okay. So, let us solve another problem. In a constant pressure cake filtration, 2 marks problem, constant pressure cake filtration, incompressible cake with an incompressible cake, that is the statement. The volume of the filtrate V is measured as a function of time. The plot of T by V versus V results in a straight line with an intercept equal to 10 to the power 4 second per meter cube. Area of the filtration is 0.05 meter square. Viscosity of the filtrate is 10 to the power minus 3 Pascal second. And the overall pressure drop delta P is 200 kilopascal. Right, the overall pressure drop, that is the delta P total. The filter medium resistance we have to find out in meter inverse. So, you see I simply in the filtration I simply remember the definition of alpha and of this Rm. So, alpha is defined as delta Pc into A divided by mu u mc, and Rm is defined as delta Pm divided by mu u. So, delta P, if you simply write, it is alpha mu u mc by area, and this is equal to delta Pm is equal to Rm into mu u. So, mu u, if we take common, so it is alpha into mc, which is V into C divided by A plus Rm, right. So, that is delta P. So, u is basically 1 by A dV dt. So, dt dV is equal to mu divided by A into delta P alpha C by A into V plus Rm. So, T is equal to alpha mu C by A squared delta P, this is Kc into V square by 2 plus mu Rm A delta P into V. So, T by V, if we divide it, we can write it like this. So, this is my intercept. Okay? This is my intercept, and once we know this intercept, all the individual values are given. So, you can calculate back what is the filter medium resistance, but you must be careful about the units. So, just I am chalking out how to calculate. Here the intercept is 10 to the power 4. So, that is equal to mu, which is 10 to the power minus 3 into Rm divided by A is in meter square, so 0.05 into delta P. So, delta P is given in kilopascal, so convert it into pascal into 10 to the power 3, right. So, 0.05 into 200 multiplied by 10 to the power 7 and 10 to the power 10, it is equal to Rm. So, it is 5 into 10 to the power minus 2, 2 into 10 to the power plus 2 into 10 to the power 10 equal to Rm. So, Rm is equal to 10 to the power 11, 1 by meter, right. So, that is the calculation for this filter medium resistance. This is probably this 2020 problem. Here, the option A is 1 into 10 to the power 9, 2 is 1 into 10 to the power 10, C is 10 to the power 11, and D is 10 to the power 12. So, my answer will be C. Okay, another question. A disk turbine is used to stir a liquid in a baffle tank. To design the agitator, experiments are performed in a lab scale model with a turbine diameter, so D1 0.05 meter and the turbine impeller speed 600 rpm. The liquid viscosity is 0.1 Pascal second and the liquid density is 10 to the power 3 kg per meter cube. The effect of gravity is negligible. If the power required in the lab scale model is P1, the estimated power for the actual application is P2. Yeah, Here the 600 rpm, 0.1, 0.001 Pascal per second liquid density is given. The actual application has a turbine diameter, d2 is 0.5 meter. This is simply a scale up problem. Impeller speed n2 is 600 rpm. Yeah, in both cases the impeller speed the same. Liquid viscosity and density, here the viscosity changes 0.1 kilopascal Pascal second. So previously it was 10 to the power minus 3. And the density mu 2, rho 2 is again 10 to the power 3 kg per meter cube. Mu 1, rho 1. So the effect of gravity is negligible. If the power required in the lab scale model is P1, then the estimated power for the lab scale, the power for the actual application is P2, and we have to find the ratio of P2 by P1. Right. So we have to first calculate, you see, the Reynolds number. Right. So RE is equal to N into d square into rho by mu. So N is 600 rpm. So 600 divided by 60 rps into d square. So it is 5 into 10 to the power minus 2 whole square into rho, that is 10 to the power 3 divided by 10 to the power minus 3. So 100 into 25 into 10 to the power minus 4 into 10 to the power 6. So this 100, this is 2, this is 10 to the power 4. So it is 25 into 10 to the power 4, much greater than RE critical for turbulent limit, and that is 10 to the power 4. Right? So we have the correlation. The power number PR is constant. It's a turbulent regime. So power number constant means P divided by rho into n cube into d to the power 5 is constant, and power is proportional to rho into n cube into d to the power 5. So obviously we will have here P2 by P1, rho 2 by rho 1, n2 by n1 cube into d2 by d1 to the power 5. Right? So rho 2 are same, rho 1 and rho 2. d2 is 10 times higher, and this is also the same. Right? So 10 times higher, so my answer should be 10 to the power 3. Let me check what are the options given. 10 to the power 3, 10 to the power 4, 10 to the power 5 and 10 to the power 6. So, sorry, it is 100 times, right? Not 10 times, no, 10 times. So, P2 by P1 is 10 to the power 3 by 10 to the power 3 into 0.5 divided by 0.05 cube into 600 by 600. Sorry, this is to the power 5. This is cube. So my answer is 10 to the power 5. Yeah. So it's typically there is no effect of this viscosity change because it is operating in the turbulent regime. But if we find this Reynolds number is less than 1, then definitely the density will be affecting, and there will be power number equal to some constant divided by the Reynolds number. So, the equation and the scale up relation will be entirely different. So, that we have to note in dealing with that. So, basically if the lab scale data or the pilot plant data is available, so you must calculate the Reynolds number and confirm the regime of this flow. Okay. A roll crusher of diameter, roll diameter is 1 meter. So, roll crusher, roll diameter, we have used the notation of capital 1 meter, are set in such a manner that the minimum clearance between the crushing surfaces is 15. So, 2D, the gap, half of the gap is D as per our diagram. So, 2D is 15 millimeter. If the angle of nip, so 2 alpha is 31 degree, the maximum diameter of the particle which can be crushed is. So, you see if you draw the diagram, if I draw the diagram once again, so this is the roll crusher, right. The particle which is nipped will be crushed. So, this angle is 2 alpha, this is R, this is small r, this is D. So, whenever this is alpha, this is 90 minus alpha. So, this is alpha, and we can write cos of alpha is equal to R plus base divided by R plus small r, right. So, cos of 31 degree by 2 is equal to this 1 meter plus D, the gap. So, D is equal to 7.5 millimeter, 0.0075, right, yeah, 0.0075 divided by 1 plus R, and from there we can solve for R, which will be the maximum diameter of the particle to be crushed. Okay. Again a scale up problem related to this impeller. Okay. A propeller of diameter 15 meter rotates at n equal to 1 rps. To understand the flow around the propeller, a lab scale model is 1 by 20th size of the actual propeller, right. A propeller diameter 15 meter rotates at 1 rps. To understand the flow around the propeller, the lab scale model is made. Important parameter to study the flow are velocity of the propeller, diameter, and acceleration due to gravity. So, important parameters are flow velocity n, the diameter of the propeller d, and acceleration due to gravity. So, these are important parameters. The rotational speed of the lab scale model that is d 2 by d1, it is 1 by 100 scale. So, let us write these are d1. So, we have to calculate what is the rotational speed of the lap scale model. So, here as you can see that rotational speed, diameter and the acceleration due to gravity is important. So, we have to keep the Froude number equality, right. So, Froude number, that is V square by Lg. So, Froude number here is pi square n square, or basically pi square we can eliminate, n square d square divided by d into g. So, n square d by g. So, it is n1 square d1 will be n2 square d2, right. So, n1 is 1 square, d1 is 15 meter, n2 square we have to calculate, and d2 is this 15 divided by 100, right. So, n2 square is 100, so n2 is equal to 10 rps. So, another problem, this is from the screen analysis. Screen analysis was carried out on a sample of gravel. The data of mass fraction and the average particle diameter of the fractions are given below. So, xi dpt in millimeter. So, xi 0.2, 0.4, this is 0.4, average diameter 5, 10 and 20. The mass mean diameter of the sample to the nearest integer. So, mass mean diameter, as we know, the mass fraction into the average particle size of that fraction. So, it is 0.2 into 5 plus 0.4 into 10 plus 0.4 into 20 millimeter. So, from there we can calculate the mass mean diameter of this particle. Okay. Next question, 2016 question this is, what we are going to discuss. In a cyclone separator used for separation of solid particle from a dust-laden gas, the separation factor is defined as the ratio of centrifugal force to the gravitational force as we have defined acting on a particle. SR denotes the separation factor. So, separation factor is basically V squared divided by Rg, that we have to note. SR denotes the separation factor at a location near the wall. S near the wall. So, it is V squared divided by R2G. That is at a distance R from the, okay, this is at a distance R from the center of the cyclone. Which of the following proposition is incorrect? SR depends on the mass of the particle. SR depends on acceleration due to gravity. SR depends on tangential velocity of the particle. SR depends on the radial location part of the particle. So, according to the definition, we can understand the answer must be A. It is independent of the mass. Okay. So, mostly we can see that problems will be either from filtration or from crushing or from this scale up related to agitation and mixing. Another scale up problem. The agitated cylindrical vessel is fitted with baffles and flat plate impellers. The power number of the system is given by Np is equal to P, this is the definition itself is given, P into N cube into d to the power 5. It is baffled flat plate impeller. Rho is the density of the fluid, n is the speed, and d is the diameter of the impeller. The diameter of the impeller, 1/3 of the diameter of the tank, and the height level is equal to the tank diameter. The impeller speed to achieve the desired degree of mixing is 4 rpm. Here what is given? The diameter of the impeller. So d is 1/3 of the tank diameter. This is the standard optimum design, and height of the level is equal to the tank diameter. The impeller speed to achieve the desired degree of mixing n is equal to 4 rpm. It is scaled in a scaled up design. The linear dimension of the equipment are to be doubled, holding the power input per unit volume constant. So this is D1. So D2 is twice of D1. H2 is twice of H1. DT2 is twice of DT1. Right? And we have to keep the power input per unit volume constant. Power input per unit volume to be constant. And that is the condition which in the previous question which you have solved during this actual discussion. And the power input per unit volume, it actually represents the degree of any mass transfer or heat transfer, right? So if you want to keep the transport coefficient constant in an agitated vessel or a tank, we have to keep the power per unit volume constant. Assuming the liquid to be Newtonian and NP to be independent of Reynolds number, what is the impeller speed to achieve the same degree of mixing in the scaled up vessel? So you see, power P per unit volume, the volume is pi into dt square into ht or h. So it is basically P, or in the order of P dt cube, and it is in the order of P into d cube. Right. So power number, here the liquid to be Newtonian and NP is independent of Reynolds number. So NP is constant. So power is equal to K into rho into n cube into d to the power 5. Right? So P divided by d to the power 3, that is K into rho into n cube into d square, that should be kept constant. So n1 cube into d1 square is equal to n2 cube into d2 square. So we have to calculate this RPM. So n2 is equal to n1 into d1 divided by d2 whole to the power 2 by 3. Right. So n1 is 4 and this is half to the power 2 by 3. So from there we can calculate it out. Acha. Next question. Consider a solid sphere, rigid solid sphere with a constant velocity in a fluid. The following data are known at the condition of interest. The viscosity of the fluid 0.1 Pascal second. Acceleration due to gravity is to be assumed 10 meter per second square. The density of the particle is 1180 kg per meter cube. Density of the fluid is 10 to the power 3 kg per meter cube. The diameter in millimeter, which we have to calculate, of the largest sphere that settles in the Stokes law regime. Maximum diameter, Stokes law regime, where the Reynolds number is also given less than equal to 0.1. So, Reynolds number, it is dP max into this velocity ut into rho into g must be less than 0.1. Right. So, ut is, according to Stokes law, is dP square rho p minus rho into g divided by 18 mu. So, it is dP max, here if you substitute dP max cube rho p minus rho into g into rho definitely divided by 18 mu to be equal to 0.1. So, yeah, this rho p minus rho into dP cube divided by 18 mu, that's equal to 0.1. So, you see this after substitution we have to calculate this dP max, which will be 18 into density viscosity, that is 0.1 into 18 into mu is also 0.1, this is 0.1, that divided by 10 to the power 3, that is rho. Now, rho p minus rho is 180 into g, that is 10, and cube root of that will be the answer in meter, and we have to convert it in millimeter. Okay. Next, see. A filtration is conducted at constant pressure. So, it is constant pressure filtration. To recover the solids from a dilute slurry. To reduce the time of filtration, the solid concentration of the feed slurry is increased by evaporating half of the solvent. That means the concentration of the slurry is getting doubled. So, C2 equal to 2C1. Resistance of the filter medium is negligible. Rm is 0. The filtration time will be reducing by a factor. So, you see here, again I remember only the definition of alpha. Delta Pc into A divided by mu u mc, and Rm is equal to delta Pm divided by mu u. So, Rm here is 0. So, delta Pc equal to delta P, and that is equal to this alpha mu u mc by A. So, delta P is alpha mu, this is 1 by A square because there is an A, into dV dt into MC, which is V into C, right? So we have delta P into A squared divided by alpha into mu, delta P into A squared divided by alpha into mu into C, it's equal to dv dt into V. So this multiplied by T will be equal to V square by 2. Right? So here that's the relation. So the fact is constant pressure to recover the solids from the slurry. To reduce the time of the filtration, the solid concentration in the feed slurry is increased by evaporating half the solvent. If the resistance of the filter medium is negligible, the filtration time will be, and recovered means you're finally recovering all this filtrate, right, all this filtrate. So in a given amount of slurry, if you are starting with the amount Vf and that is to be filtered, right, you have to remove this Vf. Now in the second case, you have reduced it to Vf by 2 because you have evaporated half. So this in the second case, it is Vf by 2. So T is proportional to V square by 2 into C, because rest of the parameters are remaining constant. So T2 by T1, or it is rather Vf, because if you integrate from 0 to Vf, it will be Vf itself, the final amount of the filtrate. So Vf2 by Vf1 square into C2 by C1. Right? So C2 is twice of C1, 2, and Vf2 is half of V1, so it is 1 by 4 into C, so it is half. So T2 is T1 by 2. So the answers where filtration time will be reduced by a factor of 1, 2, 4 and 8. So it will be 2. Okay. The next question. A continuous grinder obeying the bond crashing law, Bond's law, grinds a solid at a rate of m dot is equal to 1000 kg per hour. From an initial diameter dA or d bar A, initial diameter of 10 millimeter to a final diameter of 1 millimeter. If the market now demands the particle size, say it is dA1, now dB1, market now demands a particle size of 0.5 millimeter, the output rate of the grinder for the same power input will be reduced to. So M2 by M1 we have to calculate, P2 and P1 are same, right? So we know this P by M dot is equal to KB 1 by under root of dB minus 1 by under root of dA, right? So P remains the same. So if we write that P2 by m dot 2 is equal to 1 by dB2 minus 1 under root dA divided by P1 by m dot 1, which is here we should put the equal to 1 divided by under root of dB1 minus under root of dA. Right. Now P1 and P2 are same. So this gives you the m dot 1 by m dot 2 is 1 divided by dB2 minus 1 divided by under root of dA, 1 divided by under root of dB1 minus 1 divided by under root of dA. So you can keep this in centimeter. So 1 divided by under root of 0.5 minus 1 divided by under root of 10 and that 1 divided by under root of 1 minus 1 divided by under root of 10. So from there we can calculate the factor by which the new mass flow rate or this rate of feed is being reduced to that grinder. So we have to calculate the kg per hour. So once we get the ratio, we know this m1, so we can calculate m2 dot. In order to restore the output back here, again the second part, in order to restore the output back, m2 dot is now 1000 kg per hour. For an additional grinder is installed. This is a grinder, an additional grinder we are installing here. The two grinder can be operated either in series or in parallel. Compare the two configurations in terms of additional power consumption over the case. So what is that? Configuration 1 is series and configuration 2 is parallel. This is 1, this is 2. So what are the statement? Configuration 1 consumes less power than 2, configuration 2 consumes less power than 1, both consumes the same power. Configuration 2 consumes less or more power than configuration 1 depending on how the feed is distributed between the grinder in configuration 2. So in parallel connections. So you see, we have to go for m2 dot in both cases. And finally the size is dB2, here also it is dB2, here it is dA1 or dA, here also it is dA. Right. So intermediately it is breaking down into D1. So here the total power input is basically P is equal to m2 dot into Kb into 1 divided by under root of D1 minus 1 divided by under root of dA plus m2 dot into Kb 1 divided by under root of dB2 minus under root of d1. So this simply cancels out, giving m2 dot into Kb 1 divided by under root of dB2 minus under root of dA. Now here what will happen? Let's say we are giving out of m2 dot, m dot is here, so m2 dot minus m dot is here. And total power is Kb into m dot into 1 by under root of dB2 minus under root of dA plus m2 dot minus m dot Kb 1 by under root of dB minus 1 by under root of dA. So basically it's cancelling out, giving kb into m2 dot 1 by under root of db2 minus 1 by under root of dA. So our conclusion is both consumes the same power. Right. Both are consuming the same amount of power. So that's the idea. That no matter how we arrange this grinder in series or in parallel, they will be consuming same amount of power. And that's why the series parallel combination of grinder is only meaningful if I want to go for another types of grinder, that is crusher followed by an intermediate grinder, then a fine grinder. Okay. In Taylor series, that is a screen, Taylor series, the ratio of aperture size of a screen to that smaller screen, that is di plus 1, di by di plus 1 will be equal to what? So this is I, this is I plus 1. We know this mesh number mi plus 1 by mi is what? Under root of 2. And m is nearly equivalent to 1 by d. So di plus 1 by di will be equal to 1 by under root of 2. Right. So it is the screen to the next smaller will be root 2. That is the answer. And the options were 1 by root 2, 1.52. Next. These are 1 mark question. Size reduction of coarse, hard solids using a crusher is accomplished by attrition, compression, cutting and impact. So definitely it is compression. So then some critical speed expressions, that is simply the expression it is asked, it is a flat type of question. Okay. That is also a bond law question. See, 100 tons m dot equal to 100 tons per hour of feed, of which 80% passes through a mesh size of, so dB equal to 2.54 millimeter. 100 tons of a rock feed of which 80% passes through a mesh size 2.54, sorry, this is basically dA. 80% size is passing, that means that is the size. Were reduced to such a size that 80% of the crushed product passes through a mesh of size 1.27 millimeter. The power consumption was 100 kilowatt. If 100 tons of the same size material is similarly crushed, so 100 tons, this is M1, dB1, dA1, P1. So what is that? If 100 tons per hour of the same material is crushed from a mesh size dA equal to 5.08 millimeter to dB 2.54 millimeter, the power consumption in kilowatt. So P2 is what in kilowatt using Bond's law. So Bond's law states that P by m dot is equal to Kb 1 by under root dB minus 1 by under root dA. So the same basically M1, this is M2, M1 and M2 are same. So P2 by P1 is equal to 1 divided by under root dB2 minus 1 divided by under root dA1, 1 divided by under root dB2 minus 1 divided by under root dA1. A dB2 minus dA2 by dB1 minus dA1. So if you substitute, so this is dA1 dB1, this is dB2 dA2. So if you substitute that, you will simply calculate the power P2, right? Whereas dB2 dA2 are given, dA1 dB1 are given. So m dot has got no role to play because the m dots remain same. So that's all about the mechanical operation tutorial class. So in the next session we will be discussing about this mechanical design.